I won't be able to give a whole proof. Actually, I changed my plan somewhat, meaning that there were some steps that I consider now too technical that I'm going to skip. Okay, and I'll speak of something else that may be of more interest. But if you're not, well, I first finish what I was doing, of course, but then I speak of something else that is also related to localization and that I think may be of more interest to many of you. So the one thing I want to say, so we proved this, right? This was a simple proof. Well, remember there was this estimate I had on the board that I claimed I would prove, is that if I look at the correlator on some interval I don't recall actually what the notations are, or if anybody doesn't remember, please tell me, then I do the calling, is the limit inf when L goes to infinity, or bounded by the limit inf when L goes to infinity, of the integral over I of the expectation of the Green's function. So we had delta x h omega L minus E inverse delta y, this to the power s dE. Right? So I just want to compare this to this. Okay? So remember, this was the correlator for the infinite system, right? It's the eigenfunction correlator for the infinite system for energies inside I. And I was claiming that actually this quantity is bounded by this limit, which is for finite system. Remember, this was the operator restricted to some finite size box. And you take the Green's function at points x, y, the modulus of this powered to the power s. S is something less than 1. Right? You take an expectation over the disorder, and then you average over the interval I. So the basic formula we start with is the one I last proved yesterday, which is this. You see what is missing here is that there are two things that are missing. This is first for the correlator, right, at size L. But remember, we had a result telling us that the correlator at infinite size is actually upper bounded by the limit over L of the correlator at size L. The other thing that is missing when you want to go from here to there is that here you're taking expectation, right, over the correlator. Here there's no expectation, but of course, so the difficulty comes from the following thing. Here, when you use this relation, you have a limit s going, this is an s, not delta, s going to 1 from below. But of course, this limit is singular. This is why you have this regularizing factor in front of it. Okay? And here, well, the limit has disappeared. So how do we do this trick, right? Why does the limit disappear? The limit can disappear because of these expectations. You remember, in the proof of this, what enabled this limit to exist was the fact that when you take the s power, the integral is converging, right? But there is another way. So the integral is converging, and it's really, the convergence comes from the fact that you're integrating with respect to energy. But there is another way to integrate, which is with respect to disorder, right? And it is the integral with respect to disorder that makes this finite. Okay? So the one thing I won't do is the technical stuff that actually proves this in a rigorous way. But the whole idea is that to go over here from there is that you do the integral over the disorder in there, right? And then you perform some manipulation, which I won't describe, that enable you to remove this limit. Right? You don't need actually the limit to do the upper bound. But this is really coming from the fact that you're integrating over the disorder. Right? It's crucial that you take this disorder average. Otherwise, it's not going to work. Okay? But I won't describe this. So what I'm going to do now, what I want to do now is just to explain or prove the exponential decay I announced for this quantity, right? Which is the last step missing to get the two theorems we started from. Okay? Okay, so, and as you'll see, so what I'm interested in, I keep this formula on the board, and what I want to understand is this. So I just change the name just to, I'm going to call this, so delta x h omega L minus E inverse delta y. This I'll give a name. It is going to be G sub E super L of xy. It's yg for Green's function, right? It's just a Green's function. So it's an inverse of the operator. This is just a matrix element of the inverse. And of course, underlying this, I assume that this makes sense, meaning that this one is invertible, which is going to be the case, except at finitely many values, which are the eigenvalues of h omega L, right? This is just a matrix. And now what I can do is, well, the Green's function has one advantage, is that there is what is called, or the resolvent, right? There is the resultant equation, okay? So let me just write the resultant equation. Imagine, so remember, L is actually, because I cut things off over a cube that I call lambda L, right? I've cut the operator off over a cube lambda L, which I also call lambda. So now if I take my resolvent on h omega L minus E inverse, right? I can use the resultant equation. So I'll do it in 1D. I'll just show you in 1D what's happening. So this is a matrix. Here you're going from minus L to L. Here you have the V omega N on diagonal of, and below the diagonal, actually I have ones, okay? There is one more term on the diagonal because I have 1 minus 2D, right? Because I don't want, let me put it here. I have more space, V omega X minus 2D. So that's the matrix I'm talking of, right? Here I have 1, 1, another one. Well, I don't want the ones to mix up with my minus 2D. Need a bit more space then. So this is in 1D, the matrix I'm talking about. And what I'm going to do is I'm going to kill these two bonds that are linking part of my Hamiltonian, right? So here I have two bonds. I'm going to kill off these two terms. So what I'm saying is that I pick a point x in lambda, right? And I say that this is the same thing as h omega lambda minus x, direct sum with h omega at the point x. Well, I don't know why the lights actually go out automatically. And maybe I'm not moving enough.
To make a mistake in the demonstration.
Ah, okay. Well, it shuts me down. Okay, good. That's what is called an intelligent system, right? That's artificial intelligence, AI, at its best. Okay, and so this is minus the sum, so we are not in one dimension, x prime equal 1, of g, of h omega lambda minus x plus h omega at x minus e inverse. Here you have a matrix which is just, I call T x x prime, so it's just a matrix associated to the bond, right, linking x to x prime. And you have h omega lambda minus e inverse. Okay? I'm just using the following thing, is that h omega lambda is equal to h omega lambda minus x plus h omega x, right? So this is the operator. So this is what? It's a 1-by-1 diagonal matrix, right? So it's just a single coefficient at the point x. Okay, it's just this single coefficient. Okay? Plus tx, the sum over x, x prime, tx, x prime. Okay, this is the equation. And now you subtract energy and you multiply left and right by the inverses. Okay, and you get the equation I wrote down here. Okay, that's just a derivation of this equation. But now the important thing is that because of the block form of my matrices, right? These are two matrices. This is a 1-by-1 matrix. Easier to make it simpler. Or difficult, actually, to make it simpler. Not easier. It's the simplest one you can think of. Because of this, of course, this thing here is also h omega lambda minus x minus e inverse direct sum with h omega at x minus 1, minus e, sorry, right? This term is equal to this one, right? Because it's a block decomposition, right? The two things are acting on orthogonal spaces. Okay, and now the only thing you need to do is if you take this and do the scalar product delta x blah 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 delta y on the whole formula, right? If you do the scalar product delta x delta y on the whole formula, what do you get? Oh, actually, I'm first going to do delta x on this formula. What do I get? I get that g. So here I get the diagonal element g at e. I called it L x is equal to what? It's equal to, you see, this one acts on delta x. This one on delta x is 0. So the only thing that is left here is this simple element. So it's v omega at x minus 2d, right? Inverse, minus e inverse, right? Plus, oh, actually, I'm using which way do I want to write it? Let me think now. Yeah, I'm going to, actually, I can invert these two, right? I put this one on the other side because I have the x here and the x prime there. So what I get is I get here as a factor out g of e L at x plus the sum over the x prime minus x equal 1 of t x prime, and here it is g of e at lambda minus x, right, x prime y. Right? Why it's this one? It's because in this direct sum, using this decomposition, if you look at the point x prime, which is not x, the only term that's left over is this one. Right? So in particular, what you get here is that you can solve this equation in the sense that you extract this value from this equation, right? Extract this value. What do you get if you do this? You get that g e lambda x is actually equal to, if I do this, it's actually equal to 1 over v omega of x minus some b of x, where, and that's the important thing, b of x is independent of v omega at x. Right? The v omega at x has been killed here. It's disappeared. It's not in there. The only place where it's sitting is in here. If you solve this to extract g lambda e xx, right, you have just killed this form, right? And using this, you immediately get the following uniform bound. If I integrate this, so here I want to integrate it with respect to dv omega, right? Remember, dv was assumed to have a density, right? I called little g, right, over R. You remember, I had an assumption on my density. S is still between 0 and 1. The assumption on my density was that this function was compactly supported and bounded. Okay? So this is actually less than the sup norm of G, the integral over minus R to R of G E, sorry, look at this, 1 minus T B of dx, which is not depending on T to the power S dt. Right? The only thing I replaced this by the sup norm, that's a positive quantity. Okay? And I kept the fact that the integration interval is finite. So what you get that this is actually, we already computed this integral, this is actually bounded by some constant depending on R, G infinity. Okay, the constant depends on R and on S, of course. Okay, that's the thing I get. So that's the first thing I get. But I can also use this formula the same resultant formula can be used to obtain G lambda xy. What do I get? If I do now, I apply to the formula just on top delta x blah 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 delta y for y different from x. What do I get? Actually, maybe I'm going to do it the other way around. Which one should I take? No, that's fine. I'm going to do this. If I do this, right, so I take the formula up there on the upmost board, okay, the resultant formula, and I compute it against delta y, and I take scalar product with delta x. What do I get? I get that G lambda E of xy is equal to, well, you see, because of the block structure of the first term is equal to 0 once you take the scalar product, because they are in two different blocks, right? X and y are in two different blocks, as y is different from x. One of the blocks is consisting of just the point x. The other one is consisting of the whole lambda minus the point x. So the first term disappears. And what you get is that the second term is just G of lambda of E x x sum over x prime minus x equal 1 of T x x prime G of E lambda x prime y, okay? This is what I obtain when I take this scalar product, and I apply the resultant formula up there on delta y, scalar delta x. Okay? And now I can take an s power of this. S is less than 1. So the s power of this gives me that G lambda x y to the s is less than G lambda E x x to the s sum x prime minus x equal 1. All of these things are exactly a constant, right? They're exactly 1. So I just get rid of them to the power s. Okay? And I can do the following. I can now integrate this with respect to the variable. So I take, let me write it in this way. I just do integration with respect to the variable v omega s. Okay? What do I want to do? Oh yeah, sorry, here I forgot something. This is not this one, it's lambda minus x. I forgot to invert. It's lambda minus x. Okay, now I take the expectation of this, it's less than, expectation of this v omega x. But remember, this one does not depend on the random variable v omega x, right? I just killed it. So what I get is that actually this is less than expectation of this times that, but the expectation of this I just computed. Oh yeah, I forgot one thing. Yeah. G lambda E of x to the power s. Sorry, yeah, to the power up here, up to the power s times the sum over x prime different from x equal to 1 of g lambda minus x prime y. And here what do I have? I have e and to the power s. I get this. I forgot something because I didn't plug in my large parameter that I will need. So I'll do the integration again. Right? Remember, I had the large parameter that was actually, here I have a lambda. Forgot to put the lambda here. I'll use the lambda now. And so if I put the lambda in here, I have a lambda here. Okay? Okay? And if I change variables, okay, I get that this is, what is this? This is, here there's a lambda 1 minus s coming out. Right? I have a lambda 1 minus s coming out. Yeah, s minus 1, sorry. You're right. It's going to be small in lambda. Actually, no, that's not s minus 1. It's just s. Lambda minus s, sorry. It's lambda. Lambda. Yeah, but it's dt over t, but there is the integration. No, I think it's just lambda. It's lambda to minus s because you see, as you say, you have dt over t, and you gain the 1 power of lambda. Okay, you gain the s minus s power of lambda. Okay, and of course there is 1 minus s. Right, there's a 1 minus s. Okay, there's a 1 minus s coming here. Okay, so I can, if I put the 1 minus s, I can raise the dependence on s here. So what do we see? We have this thing. So this is some constant, I don't want to, lambda depending on s, lambda to the minus s. And when lambda is large, this constant is small. So what does this give you? Let me replace this by constant lambda minus s, right? I still get an upper bound. Okay, just replace. I still get an upper bound. And now do the following. Now define fs of xy to be the sup over all subsets in ZD of g e lambda xy expectation, right? So if now, to get the expectation of this one, I just need to integrate with respect to all the other random variables. Right here I integrate against 1, they are IID, I integrate over all the other ones. So here I get an expectation over all the other ones, which are the only ones that are coming into this operator. So what does this tell me? It tells me that this object is satisfying sum. And of course, if you take the expectation here, right, it's certainly bounded by this for the same values of x and y. So x prime y. Okay. So what you get some kind of subharmonicity condition, a discrete subharmonicity condition on the function f of x and y. But now, okay, what you can do is you can repeat this. You can repeat this. So you have x and some point y here. So you can repeat this on a path going from x to y. This is corresponding to, if you want, the Feynman diagrams that we saw in the expansion before. Okay? Well, if you repeat this, what do you get? for every step you do, going from, so you repeat this in the sense that you take the sum over here, right? So this one you can write as being less than C lambda S sum over the Z, or the X double prime minus X prime equal to 1 of S X double prime Y. As long as X prime is not equal to Y. Okay? And I repeat this. And of course, every time, what do I get? I get a factor C lambda S times the number of these elements, which is just twice the dimension, right? It's the number of off-diagonal elements that are connected to a single point, 2D, minus S, sorry, to the power X minus Y, right? Times the soup over, not S, over X and Y of this. Right? Okay, you can go on in this expansion, and you just need to take, actually, this is not, yeah, this is, I should put X prime Y, maybe, because I have an X here, and it's super X prime. Okay? But now, what do I want to say? If this soup is finite, and this number is less than 1, what did I just get? I just got that this is exponentially decaying in the distance separating X from Y. Right? But what do we know? We know that Fs of YY is finite. Right? We actually know what it is. Yes? Oh, no, it's not equal, of course. I don't want equality. It's not equal. The equal is just a misprint. Okay? So the only thing you have to prove is that this Fs x y is bounded by this, okay? Well, let me think. So I go on until I hit, so I do my expansion, until I hit the points where one of the x double prime, or at the nth step, on the xn, is going to be equal to y. And I just need an argument that actually this is bounding fxy for any x in zd, right? So, well, yeah, I need to prove this. So I won't prove this actually, but the way you have to do another computation actually to prove this result, okay? But the point is that you can replace this by fxyy. And this fxyy, we know already how to bound. This is just what I wrote on the board here, right? Here it is bounded by this. So in this way, what do you end up with? You end up with fsxy is just less than c lambda to the minus s to the d, times 2d, sorry, to the power x minus y plus 1, to make it simple, okay? And so here you have the exponential decay that you were hoping for. If c times lambda to the minus s times 2d is less than 1. The rate of exponential decay is given by the logarithm of this, right? And the size of the lambda you need to take is given by this inequality. So this gives you the lambda 0, right? And it gives you what is the rate of decay in terms of lambda. Okay, so the question you were asking, Svetlana, right?
You still have the S.
The S you choose.
Which is a parameter.
is a parameter. It's a parameter, right? You have a CS here, but you see all of this comes from this bound where things are pretty explicit, and you now optimize over this parameter. You can optimize. Here you have a bound, right? I wrote CS lambda to minus S. Now for a given lambda, I can optimize this parameter and compute what the best S is. Okay? As long as it's between 0 and 1, you're fine.
My question is, it's the proof. Does it, I mean, probably one knows at least numerically if it gives an optimal lambda.
I didn't understand the question.
Of the proof, I mean, so this gives, this gives the bound within this particular proof.
Exactly.
So the question is whether the bound is optimal.
But as I said, as long as you don't know what's happening for lambda smaller, you'll never know whether the bound is optimal or not. I mean, the only way to prove that your lambda is optimal is to know something for smaller lambdas.
No, my question is numerically, you know.
Well, numerically, I don't know. I have absolutely no idea what's going on numerically. Right? I never did any numerics. So I'm not the right person to ask, actually. But what I'm saying is that from a theoretical point of view, the only way to know that it's optimal is to prove that below this value, right, something else is happening, which is, up to now, outside reach, as far as I know. So this completes the proof, right? And so you see, many things are actually hidden in there, in the sense that, so that's one of the proofs. There are two proofs to prove things like estimates on the exponential decay of this. That is one of the proofs, and you saw inside this proof, via this resultant expansion, there is something like the Feynman diagrams coming out. But it is because here we have rank 1 perturbations. Where did we use rank 1 perturbations? It's in this formula, this very simple representation. If I try to play the same trick, right, taking a rank 2 perturbation or taking a continuous operator, there is no way you're going to be able to write it so simple, right? Nevertheless, for continuous operators, there is an analog of this method that still works. Okay? There are some conditions, of course. It's not for all continuous operators, but continuous Schrödinger operators, there's an analog of this method that works. There is another method. So this method is called the fractional moment method, and it was essentially first published in a paper by Eisenman and Molchanov in '93. There is another method, which is older, which dates back to a paper by Frédéric and Spencer, where the idea is a bit, well, it also, the idea is also resorting to resultant expansions, right? And it is actually closer to what we had in Thierry's talk, which is you have a big cube at size L, and you split it up in smaller cubes of size little l, right? And of course, little l, large L divided by little l is very large, okay? And actually, roughly, this one is exponentially growing in little l. You really have many small cubes. And the idea is, now what I want to do is I take 2 points, x and y. And the idea is to have an induction procedure, right? So you're going to repeat this over an infinite sequence of such decomposition, larger and larger each time. Okay? And what you want to do is to understand how much does the resultant, so g of large L e x y, decay between x and y when x and y are far apart. And the assumption that you make is that they decay, so you assume, right, your induction assumption, you assume that they decay in a small cube, you know that you have some decay, meaning that for little l, you know that you have g of L x y is less than e to the minus some constant mu x minus y, right? Times, there is a constant here, 1 over mu, let's say. Okay? So for some small mu, you have this. Okay? But of course, you're not going to have this. This depends on omega. These are random things. So you're going to have this with a probability 1 minus epsilon of L, where epsilon of L goes to 0 when L is large. Imagine you have proved this. Okay? And from this, you want to deduce that the same thing is going to be true with a epsilon little l replaced by epsilon large L, with mu maybe replaced by something which is slightly smaller. But what you want is that if there is a loss in mu, you want the sum of the losses not to kill the initial mu you had, right? But the mu may be slightly smaller, but not too much smaller. As I said, instead the sum of the losses doesn't kill the initial mu you had. So same thing. For large L, okay? Make it simple. It's not going to be exactly the same. There will be a small change, but the change needs to be controlled. Well, and the idea is how to go from one to the other is using a resolvent exponential like this. But you see, one of the features of this resolvent expansion, if you look at it, is that in this expansion, there's no way you can do it better if you take it finite. This term, right, which is also G lambda, appearing here, also appears on this side. The term that you are trying to control, right, is here, but it also on this side. But there is one side you want to control, and the other side, right, you cannot really extract it, because if I look at this at xy, well, this is going to be taken at x prime, because I invert it, and this one is going to be taken at x prime y. Okay? And so it's the same operator, but it's not the same matrix coefficient that you're looking at. So you will not be able in general to extract this information from the sole equation. So it means that you will need some a priori bound on how large this thing is. Because even if you know that this one is small, if you have no a priori control on how large the unknown term is, you're dead, right? Because what you want to do is, I want to write, here I have something. Here the decomposition is more complicated because I have many more cubes, right? And here I get some decomposition that there is one term I don't control a priori. I want to understand. So I need a bound. This is the one thing you will need is a bound, a priori bound, on G, E, lambda, X, Y. Okay? And this a priori bound is one of the ways, the first way actually it was used, is given by what is called the Wegner estimate. What is the Wegner estimate? It's just the following thing. This thing is certainly bounded by the norm operator of h omega L, or lambda, minus E inverse. Right? And here we're dealing with self-adjoint operators. So the norm operator is bounded by 1 over the distance of E to the spectrum of h omega L. And the Wegner estimate is telling you the following thing. Okay? It's telling you that theorem under some assumptions on the random potential, but certainly true in the assumptions I had, the probability that the distance of E to sigma h omega L be less than epsilon is less than a constant depending on the random potential times epsilon times, well, the volume of the cube, so it's L to the D. This is very reasonable. Why? It's because the number of eigenvalues in there is L to the D, or let's say in the size of it. But what is reasonable is that when epsilon goes to 0, this should go to 0. And when L goes to infinity, this probability should become large. Of course, this estimate is only useful when epsilon times L to the D is small. Otherwise, on this probability, I have a better estimate, which is 1. Okay? But it's only useful when epsilon times L to the D, when the spacing is about 1 of the inverse size of the box. Okay? Actually, you can do better than that. You can put here expectation of the number of eigenvalues of h omega L in E minus epsilon, E plus epsilon, And this is also bounded by a constant epsilon L to the D. Right? So what is actually the true Wagner estimate is this. Okay, so imagine we have this estimate, this a priori estimate, right? It means that if you have, where is it? Oh, where did I put this? It's here. If we have this at size L, right? Then if we know, right, that you're looking at an energy that is far away from the spectrum of H omega, right? Meaning that on some interval, okay, so what I said, you want to control now in this thing, you need to control the probability that this becomes large, right? So to go from here to there, what do you get? You're going to get, essentially, well, if things are well, you're going to get a path. Any path that is going from here to there is going to pass through many cubes where you have such estimates, right? And these estimates, just as in the reasoning and the scaling theory, will be multiplicative, meaning that any of these paths you're going to gain exponential decay. There will be some cubes where this is not true because it only holds with a probability 1 minus something. So you'll meet some of the cubes that are bad, where you don't get anything, right? Or better said, you can only estimate something using the Wagner estimate, okay, by brute estimation. But there are few of them because epsilon is very small. Okay, of course, you have 2 or 3 parameters you need to control together, right? So it takes really writing down things precisely if you want to be able to prove something, but the idea is that one. Now you have the number of paths, but the number of paths is not that large. It's just like some constant to the power, the ratio large L over little l. Okay? So it's going to be much smaller than what you're actually measuring here. Okay? And then you need a final control on this term, right? And in this way you can prove exponential decay. Okay? So how am I doing time-wise actually? Question to the chairman? Half an hour? Okay. Well. Okay. Okay. So in this way, that's the other method. So there are the first method, the fractional, so this is called the multiscale analysis, and the fractional moment method has the advantage of being simpler, right? And the drawback that you need more conditions on your operator, a better description to be actually able to implement it. So this one is more technical to put into practice, right? The multiscale analysis is more technical to put into practice, but it is applicable to a much wider range of operators. For example, it was applied successfully to prove localization for acoustic operators, for wave operators, for the Maxwell operator, so essentially, well, not any system, there are some conditions, of course, but many systems have been analyzed using the multiscale analysis. And there was in Germinet and Klein, so it's a 2001 paper, they set up this method, right, in some black box form. Essentially what they tell you is that if you take an operator, it needs to have some properties on its symbol, but if you take a random operator, you assume something like independence at a distance, meaning that if your operator is restricted to two different boxes that are far away from each other, not at a finite distance, but far away nevertheless, then they are independent as random variables. They need to satisfy something like a Wagner estimate, right? They need to satisfy some, what is called Combe-Thomas estimate, which is roughly that on the resolvent set you have some exponential decay of the kernel of the resolvent, right? And in the Blackbox theorem, as an output, right, you need to have, the last thing you need to have is a place to start this induction analysis, meaning have an interval in the spectrum where actually you know that for some length scale you have this estimate with a given probability, right? And so these are things you need to just check on finite scales. Okay, you have a large scale, and they tell you how large the scale is. You take all of this, you have, I think, 4 assumptions, put your operator in the black box, and out comes a theorem that says that the spectrum is localized, you have decay of eigenfunctions, you have decay exponential, you have the strong dynamical localization, with one caveat: the decay that they get is e to the minus x minus y to some power xc for any xc in 0, 1. So they do not get exponential decay, they get any type of sub-exponential decay. Right? That's the price they have to pay. You can get also exponential decay. Why do they pay this price? It's for uniformity estimates. Right? It's just, otherwise you'll have to keep constants, controlling constants. This enables you some relaxing of the constants coming in front of it. Okay, so there is such a Blackbox theorem, which is actually quite useful if you just want to know whether a system, take your favorite system, whether you want to know it's localized in some regime, check the 4 assumptions, use that theorem, and you get localization. Okay.
About dimension 1 and 2 and
Well,
then
yes.
parameter lambda.
Exactly. So about dimension 2, I don't think that mathematically there is any proof that's really different in dimension 2 and higher, right? So meaning that in the regimes where you can control, actually the initial estimate, for example, for the multiscale analysis, right, which is what you need to start with. Okay, so multiscale analysis is you start from one length scale and then propagate it to larger length scales, right? And the length scale you start with needs to have a minimal size, right? Which is actually a number which is given to you by this theorem I just quoted, okay? And so you need to check these, one way to do it is to check these assumptions, right? But to check these assumptions in dimension 2 or higher, you don't see any obvious difference, right, between dimension 2 or higher, okay? The regimes where you can check them are the same in dimension 2 or 3 or 4, so on. Of course, the numbers that you get are not the same, but the regimes, for example, edge of the spectrum, large coupling.
From a mathematical point of view, it's an open question, the pictures that we just saw.
Oh, yeah, sure. This is open, yeah, except in d equal 1.
You're saying there's more difference between 1 and 2 than...
No, there is a difference between 1 and 2, because in 1 it is proved, but using different results, that you have localization.
So you're saying in math,
Uh-huh.
there's more difference between 1 to 2,
Uh-huh.
between 2 and 3. which
Exactly.
is what was seen in the physics lab.
Yeah, sure. There is more difference in the sense that in 2 and 3, where you are equally ineffective, we don't know how to do things. In 2, 3, 4, and so on.
Do you have any opinion about what extra is needed in dimension 2 just to finish off the localization side, since we don't have to go to
Uh-huh. Well, what is needed is, so if you believe that things are localized at all energies, right, is the initial length scale estimate. So you need, so if the statement in dimension 2 is supposed to be that for any lambda, right, you have localization, well, for the multiscale analysis, what you need is, you have a certain length scale on which you need to check that for any lambda, on this length scale, you have the right decay property. And how you do that, well, I have no idea. Otherwise, I would have done it, I guess. But no, I don't know how.
Does it have to do with recurrence of...
It's not obvious, no. This is not obvious. One may try to, but I don't, there is no obvious relationship, right? No simple one, as far as I know of. There are many other ways to think of these questions, right, depending on the operator, but...
And the 1D tools just have to do with the transformation.
Exactly. The 1D tools have to do with the fact, I mean, what they have to do with is that you're looking at second order, either difference or differential equations, and the space of solutions is dimension 2. Right? This is what they have to do with. And so it's just, well, you're comparing 2 dimensions compared to infinite dimensions. Of course, 2 dimensions is easier to analyze. Right? But it's really coming up to that, and it's nothing else. Right? This is also what prevents the fact that you have multiple eigenvalues and so on. Okay, it makes everything much simpler.
Another question?
Sure, of course.
So if I make an analogy of your Green's function with what we have in physics,
Mm-hmm.
this would correspond to the Green's function of, let's say, wave equation or Schrödinger equation.
Yeah.
And this thing, I think we can show that it decays exponentially on average almost always. Except
No, what does it mean on average almost always?
No, I mean, if I take a source of waves and I put it in random medium and I compute the average field in a very weak disorder in 3 dimensions.
Uh-huh. No, but you see here the difference is that you are not looking at the Green's function without the modulus. You're looking at expectation of the modulus of the Green's function.
Okay.
Right? This makes a big difference if you don't have any oscillations. Right, especially.
Where is the modulus there?
Well, here it is.
On the left.
Well, here on the left, here it is. Where? No, I erased this. It's up there. Oh yeah, sorry. Wait, yeah, I'm sorry. I forgot. Up there, I forgot it. Thanks. That's a misprint of mine. Here, what I have, of course, I wrote it in this way, but it's the power s. Right? It's always the same thing. Of course, it's always the model. Otherwise, you don't have anything. In the sense that you don't control anything on the operator. If you just want to take the expectation of the Green's function, this one you can do mathematically as well, and you get the exponential decay, but it's of no use to control the operator. Right? It doesn't tell you anything about eigenvalues and so on. Right? It's the same thing I integrate over there. Here I wrote it properly, but sorry, I forgot about the, was a bit too fast up there. Right? Any other questions?
For the Maxwell and acoustic systems, and so why the multi-resolution method is so much better than the fractional moment? Because it's not completely visible that you cannot do fractional moments on that.
On what?
On Maxwell or acoustic or Dewey graph.
Well, it is reasonable in, well, I agree with you. No, the problem is, when you write, so here I have a resultant equation, right? And if I try to do the same kind of resultant equation for the Maxwell operator, the way the random parameters come into play is much more complicated.
Right, but you probably already have to do it to prove it by multi-resolution anyway.
Multiscale analysis? No, not in the same way, actually. You don't have to do, because performing these integrals, right? I mean, show that you actually can do some local decoupling, and this really uses the structure of the potential. If you do it for something more complicated like Maxwell, try it. You see, I don't see any obvious way to do it, right? The thing is, this really, I mean, all of this, there is one thing that's important. You really use the fact that there is an affine structure on the potential as a function of the random variables.
Right, but you're saying that the geometric resolution identity is harder, but supposedly it's already needed here.
No, but not the same properties. Of course, you use the same geometric resolvent identity, right? Or, yeah, essentially the same, but you don't use the same properties of it, meaning you don't perform the same computations on it. And of course, this changes which properties of this identity you will use. Right? It's really more complicated. I mean, this is...
Much more primitive question. When you're talking about applying this to Maxwell, the randomness is in dielectric constant?
Yeah, for example.
You're not talking about adding a potential to it?
No. It's dielectric constant or the permissivity, the magnetic permittivity, I think it's called.
Okay, yeah. I mean,
Yeah.
And if you're talking about the acoustic equation, then you have a random speed of sound? Or
Yeah, exactly. You have random speed of sound, exactly. It's not that you add potentials to it. This is why the form of is different, right?
And do these all have the property that there seems to be some critical exponent in 3 dimensions, but not one dimension?
What do you mean critical exponent?
Critical amount of disorder.
There is an amount of disorder for which you know how to prove that there is localization. Maybe it's true for all amounts of disorder. As I don't have a proof of the other regime, again, I can't tell.
But do they tend to behave similarly to the Schrödinger
Yeah, in some way, yeah, they do. I mean, for example, the acoustic operator has some very special point, which is when you have very large length scales, right? Energy 0. If you look at the acoustic operator, due to its form, right? Gradient 1 over some potential gradient. Energy 0 is a very special point, and there you don't expect localization to occur, right? Because of the form of the equation. Because roughly energy 0, you can put whatever potential, it's still in the spectrum. That's something which you cannot remove because it's a symmetry in the equation that actually conditions the existence. I mean, the fact that this energy is in the spectrum. Exactly, the constants, right? So this one you cannot get rid of, okay? And this means that actually this is very stable, meaning that what's the basic phenomenon of localization is that what you expect is that you have local, the spectrum is local data, right? So local fluctuations make the picture of your operator locally look quite different. And what you just want to escape is tunneling. You want just to escape, to take a local picture of your operator, a local part of your operator here, another one here, and you just want to show that they can't tunnel roughly because being random, it's very unlikely that they have close enough energy so that there is real tunneling between these two things, right? But of course, for energy 0 for the acoustic operator, this is completely different because at energy 0 is there everywhere, right? And so it's expected, actually it's studied, but well, not exactly the acoustic operator, but a probability study, what is called the random conductance model, and exactly around this energy. And they show that for the random conductance model. What is it? It's just take the lattice, for example, Z2, and you take a random walk where the probability to jump to the nearest neighbor is random, right? These are random parameters. And you can set it up in such a way that there is a probability to stay at a point so that the whole thing is self-adjoint. And they study the transience or recurrence properties of this operator, right, for the random walk, of this random walk actually, which in some way can be reinterpreted as spectral property near energy 0 for this thing, okay? And what they show is that actually there is some transience, meaning the walk goes off to infinity. It doesn't stay in a bounded thing, and they compute rates of transience and stuff like that. Okay, so it's not only done in dimension 2, it's done in any dimension actually. But these are special energies. Okay.
Sorry, can I ask one more?
Sure, of course.
So, are there any results beyond Klein, meaning the perturbation in the spectral gap? Are there any other regimes where
It's not perturbation. Yeah, there are regimes because there are regimes for which it's not the spectral gap, but there are regimes where you can prove edges of the spectrum where you can prove Lifshitz tails. And in these edges, right, you have Lifshitz tails, and these give you an initial estimate to start the induction.
But this is still on the edges of the spectrum.
Oh, it's in the edges of the spectrum, yeah.
So there is nothing, I mean, in a very naive question, what if we take instead of, so that requires having spectral gap to start with, right? So that means periodic, let's say A, whatever you call it, matrix, there are the constant and so on, and plus you are already in a small random.
Well, you see,
What if you just take a large random perturbation?
uh-huh.
Well, not perturbation, just large disorder, let's say. So no periodic background, just positive A, which happens to be also disorder. Do we know localization?
But what do you mean, no periodic background?
Well,
The Laplacian is a periodic background, right? So how much of the operator do you want to change? Do you want to replace the Laplacian by something else? Or the gradient. I mean, all of these are periodic, right? They're translation invariant. So any of these constant coefficient differential operators is.
Periodic background plus large disorder, not small disorder.
Well, then there are results also for large disorder, right? Meaning that there won't be any spectral. The bands may be, the gaps of the unperturbed operator may be filled with spectrum, but you still have localization in these gaps. There are results like this as well.
Even for large disorder.
Yes, even for large disorder. Even for large, no problem. Even for large disorder. I don't have the references on top of my head, but there are results like this, no question. In this case, you can actually use multi-scale techniques. There are also results relying on the fractional moment method, right, that give you localization in these cases.
Is it Eisenman and Compton?
It's possible that it's possible that you have some results in the paper of 2000 paper by Eisenman and so on in Invenciones. There are some results over there. Look at if you want to know, the book by Eisenman Varsel only does discrete models, right? But so it's a bit different. But no, there are results like this, that's for sure. I can try to dig it up if I right? Dig it up in the literature. I mean, there is quite some literature about it. But the last thing I wanted to talk about is one consequence. One consequence, there are two things I wanted to talk about. If I still have 10 minutes? Or more, great. I was pessimistic. The first consequence in the localized regime, which is actually something physicists take for granted in the localized regime, is that you have Poisson statistics for the level spacings. Right? The following. So there are theorems. I write theorem, but I put a quote here, not because it's not proved, but because I won't put all the assumptions needed to prove it, right? But the theorem is the following. Take your h omega L, right? So this has only finitely, again, I speak of the Anderson model, right? So you have E of omega and L. These are the eigenvalues. Right? Remember we had L to the 2D. No, sorry, L to the D, it would be better. My cube is minus LL to the D, 2L to the D, right? And then you have a quantity. So the first I didn't introduce yet, but it's the integrate density of states. Well, I guess you all know what it is. You just count the number of eigenvalues divided by the volume, right? Well, take the limit when L goes to infinity. This limit will exist. It's going to be a function which is almost surely independent of omega, right? So almost every omega for energies here, you are going to have this thing, it's a function, nice function, which of course this side is increasing, so this one better be, or it's not decreasing, so this side better be non-decreasing as well, right? And because of this number, we know that n of E is the probability distribution, is it's the distribution function of a probability law. What does it mean? Well, it means that n of E takes values between 0 and 1. It's increasing, and actually the support of the measure, dn of E, so you take the differential, distributional derivative, right, is going to be the almost sure spectrum of your random operator. Okay, the points of increase of this thing is the spectrum of the operator, the almost sure spectrum. So, and the theorem I wanted to speak of is the following. Now do the following. Take the following random process. You take n, you take the images, right? Take the images of the eigenvalues through the density of states. So this gives you points in 0, 1, right? These are points in 0, 1. Now, you renormalize the typical spacing, as you already saw, is 1 over the volume of the box, right? Or if you want, 1 over the number of these points, because you have so many points in 0, 1. So the typical spacing is 1 over the number of these points. And you fix some little e, and you take the process, right? Take the process, so e is fixed, right? And take the process sum over n. So this is a random process, so it's a random point measure on the real axis. Yes?
You really want that n here?
This one?
The capital N.
The capital N is just this function. I take the image. You see, you have the real spectrum, which is on some set you don't know and you don't care about. And you use the mapping n to bring in on 0, 1. I'm changing variables, exactly. To bring it as points. So here you have the e's, right? The en, and you get them to points on 0, 1. Right, so you have points here on 0, 1 that are still random points. Okay? And this way you coin up this point process. Okay? And the theorem is that for any e in 0, 1, this thing converges weakly to Poisson process on R of intensity 1. So these are infinitely many points that are uniformly distributed on the real line. And what is this Poisson process? This is exactly what you would get. What you get when you replace n of En by IID with low uniform on 0, 1. Right? Uniform on 0, 1 dt. If you do the same computation and replace the random eigenvalues by uniformly distributed random variables on 0, 1 that are independent, you get exactly the same result. So interpretation, the eigenvalues behave like IID random variables, and the distribution is just the density of states. Right? This is well known to physicists, and there is a famous dichotomy in physics, which is that in the localized regime, it is in this way, right? You have Poisson statistics. And in the delocalized regime, it's supposed to, the same quantity here is supposed to follow, depending on the class of symmetry of your model, the GOE or GUE random matrix theory. Of course, as for mathematics, the second part of this dichotomy is not known, right? Well, except for one thing that I wanted to come to. Okay, you can prove also, there's another thing one can do. So this was first proved, the one I have here for the Anderson model was first proven this result for Minami, by Minami 20 years ago, a bit more than 22 years ago, 23 almost years ago. You can also do something else. You can study the level spacing. You can study, right, which is not exactly the same thing as this. You can look at the level spacing, so that is the difference between the level to the next, right? And if you study the empirical histogram of the level spacings, well, what you obtain is also that it is the same as the one you get for the IID random variables distributed according to 0, 1. Okay? And this for a very large class of random operators. Yes?
Is it known for Bernoulli?
Sorry?
Is it known for Bernoulli? What's the
No, not that I know of. Maybe someone has it in its pocket, but no, not that I know of.
We've seen, I mean, Doug has done the computation for some point. It's a very interesting sort of fractal pattern.
Well, I imagine that it...
Imagine where it comes from
No, no, but it may take actually very large samples to see it, right? So how fast this converges to this low is another story, right?
It's not that bad. I mean, you can definitely see something which is stable on the computation.
Uh-huh.
On the
Yeah, that's interesting, actually. That's interesting.
Case with 19 million random numbers.
Okay, 90 million random numbers is a pretty large sample, to my opinion.
So from the skin cloud, and it already was pretty stable. So it's not that.
But I'm pretty sure that the situation is much better if you take a smooth distribution, isn't it? That you get a much faster convergence. I don't think there is any result on how fast it converges, but I would imagine that if you really take...
That's not the question. I mean, when you take smooth, you get Poisson, and Bernoulli definitely doesn't go to Poisson. So
Or it doesn't go to Poisson at all.
it doesn't go to Poisson at all.
Or is it just that the sample is too small?
It's pretty stable, so it looks like it's actually, well, possibly always.
It's a good question. It's a good question. It's true that for Bernoulli there are things that are missing. For example, Wegener is not true. So Wegener is a basic ingredient in there. And there's another estimate called the Minami estimate.
Not true or not known?
No, not known, that's for sure. This I can put my hands in the fire. But not true, this, well. Sorry?
You believe it's not unknown?
I don't know. I don't have a proof. Neither of this nor of the contrary, so. I stick to the standard way of doing in mathematics, right?
For the GOE case, so you're saying there's no proof.
Yeah.
Is it some kind of conjecture? Like
Well, the conjecture is the one that's coined up by physicists, right? But the conjecture is the one that was coined up by physicists, so it's that when the thing is delocalized, it's GOE. But I wanted to say something about this. There is one model that was successfully studied by Eisenman and Warzel, which is not the lattice, the square lattice, but which is the beta lattice, right, or the tree, the regular tree. So let's take a connectivity 2 regular tree. Okay, and you can do the same things, meaning you take the adjacency matrix, which is a Laplacian on the regular tree, and add a random potential at each of the vertices of the tree, right? And I cut it short. Imagine that your random variables are infinitely distributed in the sense that they're not bounded, okay? And I draw you the phase diagram that they found. Okay, so this is, it's essentially, it's up to what I'm going to tell you, it's a theorem, right? There's a phase diagram. So, in the vertical axis, I put the coupling constant. So they put the random variables, for example, are Gaussian. Okay, take Gaussian random variables. Okay, meaning the potential on the vertices are Gaussian random variables, IID. Okay, but nevertheless, they carry a coupling constant in front of them. Okay. The coupling constant is just measuring the size of the variance of these random variables. Okay, they're Gaussian normalized, meaning expectation 0. Okay, normalized is in this sense. Well, what they showed is that here you have pure point spectrum. So here we have the spectrum. Sorry, the spectrum. So this is this coupling parameter, right? So the potential here at the edges is lambda v omega x, where v omega x is Gaussian, E of v omega 0 is 1. Okay? They don't need it to be Gaussian. It's just to make it simple. At lambda equals 0, the spectrum of the operator, so this is k equals 2. K is the connectivity. It's the connectivity of my tree, right? So it's the number of edges starting from a given vertex. Okay? So let me put it. Actually, I don't remember whether it's the number of edges going upwards or it's the number of edges altogether, right? So it's either k or k plus 1. So this is k equals 2, right? Connectivity is going upwards. So here you have square root, the spectrum at lambda equals 0 goes from minus square root of k to square root of k. In the blue region, you have pure point spectrum, right? And exponential localization for the beta lattice. And here, there is another blue region, right? Where you also, sorry, there is not another blue region now. I think I have it mistaken. Let me get the graph again. Oops, where is it? There is not the blue region, sorry, it's another region. Well, there is a special region, let's say yellow, but this is also AC spectrum. Here you have AC spectrum, right? So it's delocalized. the yellow region, this is why I mark it yellow, you have only AC spectrum. In the blank region, you may have AC and something else, but there is AC spectrum in there, right? There is AC spectrum. And the funny thing is, now you can compute the Poisson the statistics of the levels, right? You can compute the level statistics, the one I just introduced for this graph, meaning that you take a finite part, so you have the root, let's say 0, and you take a finite subgraph, right? And you compute the statistics for the finite subgraph and let this grow in the same way as before. And what you find is that here you really have Poisson statistics, but here you also have Poisson statistics, even though you have AC spectrum.
So what does it mean, Poisson and continuous? How does it?
It means the following. You take, here you have a finite graph, right? But this finite graph, it's a finite matrix. So you have eigenvalues. So you can do exactly what I did here. Take these random numbers and do exactly the same thing. It converges also to Poisson. So the dichotomy I was speaking of, that pure point means Poisson, and AC means GOE, depending on the symmetry class, well, doesn't seem to hold, right? There is a caveat, you have to, because if you think of the graph limit of this, when you let the size of the ball grow, it is not the infinite beta lattice. It is what is called the canopy tree, which is the following. You start from infinitely many points, and so on, right? And then you join them. Right? It is the limit of this when you start, fix this point, and you see it growing in this direction. And this canopy tree, as its spectrum, has only pure point spectrum. You see, when you take the limit of a graph, of these infinite, of a sequence of growing graphs, you have to be careful of how you fix, because of the fact that they are, well, not symmetric, right? You have to be careful how you consider the limit, right? And so the limit of this one, when you're measuring the statistics here, the true limit of the graph that you should look at is this graph here, right? You can go on. So I hope you see what I mean, right? It's just you take this, and next generation you keep this point, you put it at 0, and you let it go on, and you go to the infinite. But this graph here has only pure point spectrum. Why? Because you see that by taking a single branch and erasing it, you disconnect the graph into pieces, right? So this goes, here you have another one, here, this one goes here, and you go on this way, right? You disconnect the thing into pieces that are of finite size, right? And so this is why this has pure points. So this is just to underline the fact that if you want the conjecture to be correct, that Poisson corresponds to pure point, and AC corresponds to, or GOE corresponds, or GUE corresponds to AC, you have to be more precise than just taking a random operator on any set. There is something more to analyze. It may be true. You have the same phenomenon. There is a famous conjecture called, if I remember well, the Bohigas-Giannoni Schmidt, conjecture, which is the following. You take a chaotic classical system, right? For example, a billiard, okay? And you look at its large, so it's a compact manifold on which you look at the Laplacian, and you look at its large eigenvalues and look at the level spacing of the large eigenvalues, And this should converge to the level spacing of GUE. Okay? Well, again, the only mathematically treatable systems of this kind, which are essentially arithmetic manifolds, right, show a different behavior. Meaning that they converge, if you look at their statistics, they converge to Poisson. So, but of course, these arithmetic varieties is a bit like when you are fishing a real number at random. Chances are that even though the rational numbers are only measure 0, you end up with a rational number. Right? If you have to choose yourself a number in the real line, yeah, well, good. Can you tell me many others? Not constructed on pi and the exponential? So, of course, pi square. So you see, again, so there are, just to say that the physical conjectures maybe should be phrased in a cautious way, right? Saying that it's going to be true for many systems, right? But of course, one expects that there will be systems that still show one behavior, not the other one, right? And I think my time is over, and I stop here, and thank you for your attention.
Let me understand.
Yes.
In the Eisenman-Barzel analysis,
Yes.
it's the way they take the limit from the.
No, no. What the analysis shows, it's not that they take. What the analysis shows is that the right way to looking at the limit of this graph is this one. This is what the analysis shows. I mean, you fix these graphs, right? For every L, you have one. For every size of a ball here, you have one such graph. Okay? There's no choice. This is a given. Okay? You are fixing the random variables. Huh?
The distance is just literally how many steps out.
Exactly. The distance is just how many steps out.
Yeah.
Right?
And it turns out that the appropriate limit is.
Exactly. It turns out that the appropriate limit you should think of is the canopy tree, but not the infinite tree itself. Where does this come from? It comes from the fact that if you look at the volume of the boundary, right, it is of the same order as the volume of the whole thing. So the real effects are happening on the boundary. And on the boundary, the thing here is, so you should look at things from the boundary. But from the boundary, this is the canopy tree, and not the other one. Right? This is where it comes from. Yes, please.
There are some models
Uh-huh.
for which the disorder has special symmetries, like when you wrote what I call the tight binding,
Yes.
the discrete one, you put random hoppings.
Yes,
Then, as you said, there is a special energy, which is energy
that's
zero,
correct.
where the system, I don't like to say it's delocalized.
It's not
The
delocalized.
wave function decay as an exponential of minus square root of x.
Okay.
Not exponential of minus x of xi,
Uh-huh.
but only exponential of minus square root of x. So formally psi is infinite. So how?
Well, as I said, there are some works. I don't think that there is any real mathematical result on the form of the zero energy wave function, right, for this system, for a random system like this. But there are results in probability theory that go into this direction in the sense that they show that if you take this, so this can be, if you choose the parameters properly, this can be associated to a random walk with random hopping, right? And they show that this random walk is transient. So the random walk goes off to infinity and doesn't come back, which exactly, well, it's not exactly this, right? But it's some indication that you have this large correlation in eigenfunctions corresponding to these low-lying states. Right? But I don't know of any result showing that the eigenfunctions display this behavior. Maybe in one dimension there is something. This is, but
I know you can connect it somehow to Sinai model, at least
Uh-huh.
by physicists.
Yeah, I know.
It's
Yeah.
not figures.
Uh-huh. No, but maybe for one dimension there are things known. But it's known, for example, it's known that you have some special energies when in 1D where you have something which is weaker than what you just said, is that you have zero Lyapunov exponent, right? And these zero Lyapunov exponent also exist for Schrödinger operators if you take reflectionless, right? If you take reflectionless in one dimension, right, you can speak of a reflectionless at certain energy potential. What it means that at this energy, actually, if you take a wave at this energy, just go through the barrier without seeing it, and you take such reflectionless potentials, take a random thing of them, then you can get energies that, well, some energies may be special or reflectionless, but they happen to be single points. So there is not enough space to carry AC spectrum. Right? I mean, a single point can hardly carry some AC measure, with respect to Lebesgue. But nevertheless, you find that at these energies, the Lyapunov exponent do vanish, and there is some special behavior of transport. This was analyzed for dimer models, for example, at these energies, but mathematically, I mean, right? And it's analyzed mathematically, so there are theorems proving that you have special transport exponents. Transport exponents, what does it mean? It means that if you prepare a wave packet near these energies and look at the evolution under your operator e to the minus ith of this wave packet and look at how the position operator, meaning x times this function, grows. When x grows, it doesn't grow, well, it actually, sorry, it grows and it doesn't stay constant like in the localized regime. Right? So this was done. This was proved in the 90s, I think. Well, you're going to speak.